Hello, it's Josh here. Happy Friday. I hope you are all having a nice day off of class. Yesterday, before we got into the quiz, you'll remember that we did a Riemann sum calculation within a sigma notation, and it was fairly technical. And I was thinking this morning that perhaps giving you a secondary example of this is not such a bad idea. We will look at this more in the next into next week regarding limit calculations, which I know we haven't addressed yet. But I think it's important to be able to see and understand how the algebra is working. So I've included this video. You can use it at your leisure. Certainly, if you choose to use it, I hope you find it somewhat helpful. So I have this problem prepared. It says consider f of x equals x plus 1 on the interval from 2 to 4, and we're going to find the midpoint Riemann sum for n equals 100. Yesterday's example, you'll recall, was something like n equals 8, and my last point of the day was probably that some of you might have done this without the use of sigma. So what's the benefit in sigma? Well, for an n value of 100, certainly we're not going to want to write out all the terms of the sum. And so the nice thing about the Riemann sum is that if we know how to find delta x, as in this instance b minus a over n, and we know the b and the a value is the given 2 and 4, or 4 and 2, and the n value of 100, then suddenly 2 over 100, or 1 over 50, I have a nice width of each subinterval. So we're looking at 100 subintervals, each of width or length 1 over 50. And in the midpoint Riemann sum calculation, one of the definitions I gave you in class yesterday, before we got into our problem, was that the midpoint Riemann sum is found by taking a and moving k up by what I would consider half steps. And so we take a plus k minus a half delta x. Well, in this instance, our a value is going to be 2, and then we have k minus a half times a delta x of 1 over 50. And that's an okay thing to consider. If you want to multiply it out, though, you would get 1/50th k minus, what would that be? 1/2 times 150 would be 1 100th. And if you combine the 2 and the 1 100th, 2 is 200 over 100. So you'd get something like 199 over 100 plus 1 over 50k. So a midpoint Riemann sum input for each of the particular subintervals is going to look something like that. And if you'll recall, the general Riemann sum we found out was the sum from k equals 1 to n of your f of x sub k star delta x's. So this is the standard approach. In this case, we're going to be looking at an n value of 100, so it'd be the sum from k equals 1 to 100 of your f of 199 over 100 plus 1 over 50k times a delta x value that we found to be 1 over 50. So we're slowly moving from the general standard way of writing a Riemann sum for any n value to our specific Riemann sum and a specific function with n values of 100 and a function value f of x equals x plus 1. So where do we go from here? Well, I've also included on your screen a little bit of the sigma algebra. So in this circled enclosed area, we have some of the sigma algebra from yesterday. So where we would go from here, my general recommendation would be to get a better idea of what f of 199 over 100 plus 1 over 50k looks like. In this instance, the function is x plus 1, so we're going to take 199 over 100 plus 1 over 50k, so that's our x value, and we're going to add 1 to it. Well, of course, if we add 1 to 199 over 100 plus 150k, we end up with something like 1 is 100 over 100, 299 over 100 plus 1 over 50k. So rather than have that notation f of 199 over 150k, what that really looks like is going to be the sum from k equals 1 to 100 of 299 over 100 plus 150k, I keep saying 150, 1 over 50k, times 1/50th. So if we can then turn this into a numerical value, the idea is that the midpoint Riemann sum using n equals 100 on this particular function in this interval, that's going to be an approximation to the area or the midpoint Riemann sum for that value. Okay, so how does then sigma algebra allow us to proceed? What I did yesterday is I went and put the 1 over 50th, or the 1/50th, I would put it into the two-term sum inside. I'd get the sum from k equals 1 to 100 of 299 over, what's 100 times 50? It would be 5,000, and then that would be plus 1 over 50 squared, so it's going to be 25 with 2 zeros, 1 over 2500k. And here is where the sigma algebra from the circled area is going to come into play. We learned that the sum of one thing plus a different thing inside the same sigma can be thought of as the sum from, say, k equals 1 to 100 of 299 over 5,000, plus the sum from k equals 1 to 100 of 1 over 2500 k. And then within each of those individual sigmas, in the first case, as the counter k is changed, you'll notice that 299 over 5,000 never changes. And so we would say that this is constant with respect to k, and that's where this comes into play. The sum of a constant is actually 299 over 5,000 times the number of steps in the sum. Well, counting 1 up to 100, that's 100 total steps. So we get 299 over 5,000 times 100. On the other side, it's not quite as straightforward. The 1 over 2500 is multiplying something that is changing as k changes, but that's going to make 1 over 2500 a constant multiplier within a summation input. And what we're allowed to do with constant multipliers is we are allowed to pull out the 1 over 2500, giving us the sum from k equals 1 to 100 of that k. Now, here's where that individual property that we proved somewhere during class yesterday becomes important. We know that the sum from k equals 1 to n of k is n times n plus 1 over 2. So in our case, what I'm looking at in the circle box here has an upper n value of 100. So we end up with 299 over 5,000 times 100 plus 1 over 2,500 times 100 times 100 plus 1 over 2. That's what this property here tells us, 100 times 101 over 2. And lo and behold, this is something that I should be able to break down in some way. If I look carefully, first and foremost, the 100 and the 5,000 are going to cancel down. Basically, 2 zeros divide out of the bottom, giving us 299 over 50. And then on the other side, let's see what we're looking at. We're looking at the 2 and the 100 are dividing, giving us 50. And then, so what do we have? We have 50 times 101 over 2,500. And so, of course, the zeros may cancel down. And then if we take 250 and we divide it by 5, we get 50. So we get 299 over 50 plus 101 over, again, 5 on top of 250 gives us a 50 denominator. And it turns out that what we're looking at is, let's see, 299, so we would get 400 over 50. Am I doing my math right? So 299, 399, 400. So 400 over 50, and 400 over 50 is going to give us something like, what is that, 8? So 50 goes into 100 4 times. Oh, I'm sorry. No. 50 goes into 100. No, I'm sorry, 2 times. So it is 8. This is somewhat a surprising solution given how technical the input was. So yeah, 8 times 50 is in fact 400. So from start to finish, again, fairly technical, but I did think it might be important to see this a second time in the event that what we did in class wasn't clear to you. So hopefully now you believe that the method we used yesterday can be a little more efficient, especially for large n. In this case, I would never want to take a base and a height and multiply them together 100 different times and add up those 100 individual results. But what happens here is if we have a nice formulaic midpoint setup, we can embed that into the original function and then create what amounts to a general sigma from sum from k equals 1 to 100 that algebra allows us to then manipulate down into a nice value. This doesn't necessarily mean that the exact area is 8, but it gives us a fairly decent approximation. The bigger the n value, the better the approximation, and so we can feel fairly comfortable that n being 100 is significantly larger than 8 or 10 or 20, so it's going to be a decent approximation. And we'll talk in the coming week about how we go from an approximation to exactness of the value. So thank you for your attention if you chose to use this as a supplementary exercise. Hope you have a wonderful rest of your day and a wonderful rest of your weekend, and I'll see you guys on Monday. Take care.